Illuminated by IEEE Photonics is a podcast series that shines light on the hot topics in photonics and the subject matter experts advancing technology forward.
Hi, everyone, and welcome to today's episode of Illuminated. I'm Akhil, and as the past Associate Vice President of the Young Professionals, it's my pleasure to be your host today. I'm a biomedical physicist and engineer working at the University of Strathclyde as a Chancellor's Fellow and a Leverhulme Early Career Fellow. In my role for the IEEE Photonics Society, I support and promote initiatives, much like this podcast, to raise the profile of valuable young professionals within various sectors. The Young Professionals Initiative is for graduate students, postdoctoral candidates, and early career professionals up to 15 years after their first degree. This affinity group within the IEEE Photonics Society is committed to helping one pursue a career in photonics. We're here to help evaluate your career goals, better understand technical pathways and subject matters, refine skills, and grow professional networks through mentorship. It is very interesting to have this conversation today as the Photonics Society turns 60 in 2025. The timeline experienced by the IEEE Photonics Society includes 6 decades of innovation, growth, and leadership in the field of photonics, making a journey from its origins in quantum electronics to becoming a global leader in photonics technology. On to our podcast. In this podcast, we're chatting with Professor Sir David Payne. We'll reflect, along with your host, Dr. Richard Pitwin, on the last 50 years of optical interconnects, fiber technologies, optical communications. We'll look at the evolution of ECOC as a conference that it is today. We'll talk about Sir David's experiences as a knight, experiences outside science throughout his career. Let me introduce Richard first. Dr. Richard Pitwin is a director, scientist, and engineer who has been instrumental over the past 25 years, mostly at Seagate, in the development of system-level optical and photonic technologies, in particular for hyperscale data center environments, which are the bedrock of modern AI infrastructures. Today, he's the CEO of Resolute Photonics, which he founded in 2018, developing specialized photonic integrated circuits and subsystems for communication, sensors, and quantum and space applications. He's also a chartered engineer, fellow of the Institute of Physics and the IET, and has over 55 patents on a broad range of technologies. He's the current chair of the IEEE UK and Ireland Photonics chapter, and also the chair for many international standard committees in the BSI and the IEC on fiber optics and connectors. He recently established and now chairs a new committee on optical interconnects, on quantum optical interconnects in the IEC, which will develop the standards for the next generation of very sensitive fiber optic connectors and extremely low loss optical fibers. Over to you, Richard.
Thank you very much, Akhil. So it's my great pleasure to introduce Professor David Payne, who I've had the privilege of knowing for over 15 years. Now, this is my first podcast, and to help me frame my introduction, I read David's online bio, and it starts with the sentence, Sir David is an internationally distinguished research pioneer in photonics, having been in the field for over 50 years. Well, I'd say that this is probably one of the great understatements of the last 50 years. Now, this year we celebrated the 60th anniversary of the internet. I mention this because outside the photonics community, not many people will have heard of David Payne, and thus not many people will know that without his work and the work of his many colleagues over the last 50 years, there would simply be no internet. There would be no telecommunication as we know it, no means to convey the vast amounts of information over long distances that we take completely for granted today. And this is not an exaggeration. And the reason for this is optical fibers. Optical fiber technology is one of the greatest scientific successes of the last 6 decades. And as we'll be hearing today, David Payne's role in the formation and evolution of optical fiber technology has been indispensable. Now, David's pioneering work in optical fiber fabrication in the 70s resulted in almost all the special fibers we use today. He led the team that in 1985 first announced the silica fiber laser and the Erbium-Doped Fiber Amplifier, EDFA. And the EDFA is widely regarded as one of the foremost and most significant developments in modern telecommunications. And that work, that invention, singularly fueled the explosive growth in the internet by enabling the transmission and amplification of vast amounts of information. Now, I won't list all the awards because there simply isn't enough time, but I must mention that in 2013, he was knighted for services to photonics in the Queen's New Year's Honours list and became Sir David Payne. And in 2018, with his colleagues from ORC, he won the Queen's Anniversary Prize that celebrates excellence, innovation, and public benefit in work carried out by UK universities. Now, the theme of this podcast is past, present, and future, with focus on the anniversary of the internet. And I think we have 90 minutes, and that's barely enough time to scratch the surface, especially with someone like yourself, David. But I'm gonna try. Now, along with your amazing colleagues at the ORC in Southampton, you're responsible for most of the key technical achievements which underpin the old, current, and future internet. And these achievements span diverse areas of photonics, which we'll touch upon in this podcast, from telecommunications, that's your seminal work in optical fiber communication, sensors and optical materials, to nanophotonics, in particular silicon photonic integrated circuits, which now form the basis of all modern optical transceivers, optical storage, for example, the famous 5D optical storage in glass, which you can store information till I think the end of the universe. And I hope we talk about that as well. All of these form part of a vast ecosystem which underpins the modern internet. So let's start at the very beginning. And sorry for the boring question to start you off, but when did you first start working on optical fibers?
Well, thank you, Richard, for that very generous introduction, and I'm really excited about this opportunity to provide my thoughts on past, present, and future. Starting with the past, I believe I was actually the very first PhD student on optical telecommunications in the wake of the famous Charles Cow publication. So I started my PhD in 1967, and under the great Professor Alec Gambling. And he came to me and he said, well, why don't you do a PhD? And I said, well, I'm not really planning on doing that. I want to go into industry and do some real stuff. And he said, well, we've got this really interesting project where we want to create optical fibers that will span the globe. And this intrigued me. So I said, well, sounds an interesting project. How far would you like to go? And he said, yeah, maybe from Southampton to London. And I said, okay, that's about 100 kilometers. So how far can we go at the moment? And he said, maybe about a meter. So this was a challenge which only the arrogance of youth would step up to. And indeed, within a few years at Southampton, with our makeshift fiber drawing machines and so on, we had actually got the world's record of the lowest loss fiber ever since. And I found myself in the midst of this maelstrom of development and excitement as we fiberized up the entire world to create what today is called the internet. So that's how it all started.
Well, you mentioned Sir Charles Cow. Charles Cow, I believe his seminal paper in 1964. He's basically, I think it's safe to say, he's the father of optical fiber technologies, and I think you knew him very, very well.
Yes, that's right. I was extremely privileged to know Charlie extremely well, and partly because, of course, his work was done here in the UK at Harlow, Essex, which was standard telecommunications laboratories there, and he did his seminal work there, describing how we could use silica as a means of communication. And frankly, everybody thought he was crazy at the time, because everybody else in the world was working on microwave guided waves, the H01 waveguide, for example, in copper, and Bell Labs, the great Bell Labs, which usually led the world, was actually working on a lens system, periodic lenses every few kilometers, refocusing a light beam. And Charles said, no, we can do this with silica. And you've got to remember that in those days, one had no idea of the loss of glasses, because nobody had ever measured them at the ultimate limit of how low loss they could be. And take an example, the average window would only allow something like 90% of the light through it. So you're losing 10% just to the thickness of a window. And what Charles proceeded to do was to select silica, which was an amazing prescient thought, and then proceed to show that it had losses below 20 dBs per kilometer, which, when you think about even today, is an incredibly challenging thing to measure in the lengths available, which were maybe 10 centimeters or something like that. So this is why Charles got the Nobel Prize, but also he was a great advocate for optical telecommunications. And he toured the world telling everybody that this was the way to go. And everybody said, no, Charles, that's never going to happen. But look where we are today. We have 1 billion kilometers of silica fiber installed.
Actually, I looked this up this morning, and it turns out it's more than 4 billion kilometers. So it really scales up really quickly. And that is the distance to the sun and back 22 times. And that's the distance to Neptune, our furthest planet. So that shows you the incredible impact of optical fiber technology. You mentioned that. Oh, go on. Sorry.
Well, interesting that those numbers. So Corning Glass and YOFC in China both celebrated this year their 1 billionth kilometer sold. So that kind of adds up, because those two companies probably have about half the world's market. So, and the current installation rate is at about 500 million kilometers per year. So this is just an amazing achievement.
You mentioned losses. Of course, one of your most notable achievements is the Erbium-Doped Fiber Amplifier. Can you tell us what led to that breakthrough?
Yes. One of the things that has characterized our work at Southampton is that we are very aware of what it is that the market needs. And that's a number of people have remarked that that's quite rare for a university. Universities tend to do the more fundamental research without paying too much attention to the marketplace. And it became very apparent in the early 80s that we could get through about 100 kilometers of fiber before the light dimmed, and there was insufficient light to overcome the noise of the detector. And what you needed to be able to do was to boost the light back up again, because the alternative was to detect the light and use an electronic amplifier and then retransmit the light. And it's not rocket science to figure out, well, the problem with that approach is, first of all, the electronics is nowhere near as fast as the optics. And secondly, electronics detectors cannot distinguish between different colors of light. And so scrambles them all up. It therefore was apparent worldwide that we needed an amplifier. So a lot of people started to work on things like semiconductor amplifiers, on Raman amplification, and we started to think about these matters as well. And it's interesting to note that we actually came out of a laser group at Southampton. So we were late to telecommunications, but our roots was in lasers. And so it didn't take us very long to think about, well, a laser is an amplifier with feedback around it. So why don't we think about doing that? And we started to put rare earths. I have to confess that at the time we were driven not just by amplification, but by sensors. And a lot of our early work was on making a distributed fiber sensor, which was also another Southampton invention, using rare earth doped optical fibers. And then we hit on the idea that we could make erbium lasers. And here's a little anecdote that I don't often tell. We were actually making lasers because that was our roots, right? We wanted to make lasers. And one day, the PhD student, Robert Mears, took the mirrors off the laser, the erbium-doped laser, and realized that the gain was in excess of 20 dBs. We all got very excited and jumped up and down about this and said, well, you know what, this is going to be an amplifier then. And it took a while for us to fully sink in because all of the other attributes of a fiber amplifier compared to the competing diode amplifiers and the Raman, which are the very slow gain dynamics, meaning that you pump the thing up and then the signal that is coming through it doesn't change the gain very much. And in these other devices, you get a modulation of the gain depending upon the magnitude of the signal. That's obviously undesirable. It tends to mix up the channels. So, it was also realized that it's polarization in agnostic, and it was extremely efficient, and it required a very small pump, and so on and so on. And the rest is history. But the anecdote I was about to tell is that we published 27 publications on erbium-doped fibers before we realized it was going to be an amazing amplifier. And we announced that in 1987, January at OFC, etched in my mind. And of course, the world largely said, nah, it's never going to work. Because at the time, it was pumped by 100 kilowatts of argon laser, because that's the only source we had. And Bell Labs, my old friend Emmanuel de Sevilla, followed immediately afterwards. And because he had the fibers and he had the laser as well in his labs. Equally, his took 100 kilowatts. But, the next big step was to make it diode pumped. And actually, it was BT that did the first diode pumping, and that's not widely recognized, largely because it was not very efficient, and it was done at 800 nanometers. Before the Japanese came in with 1480 pumping, but it was 980 nanometers, and it was Southampton in collaboration with Bell Labs that did that first and pointed out that that was the way to go. And the world today uses 980 nanometer pumping and erbium-doped fibers in every amplifier. And even today, after more than 30 years, there's no serious competitor to the erbium-doped fiber amplifier, the basis of the internet. As people have often said, you know what? What it actually did was it made us globalize networks. Networks up to then, because we could only get through 100 kilometers or so, were small. I often joke that's why they're called local area networks. And then it was became WANs, wide area networks, because we now had amplification and we could get across an ocean. So it became one network of a global size. And maybe the next big thing is to make it intergalactic, but I don't think we're going to use fibers for that.
Well, funnily enough, there is a call now for low Earth orbit satellites are so ubiquitous now for communication, and they need such high bandwidths within them. There is the emerging need for optical transceivers within for communication within satellites themselves. So transceivers and fibers within the enclosures of satellites, simply to accommodate all these high bandwidths of information. But these transceivers need to be completely space resilient. They have to survive cosmic radiation, high energy particles, and fibers, of course, are fantastic for that. Fibers are very radiation hard. the weak points of the transceivers and the lasers there, which if you have quantum well lasers, they can be destroyed by a well-placed high-energy particle and so on. And that's why we're seeing innovations such as quantum dot lasers, I think, where you get these redundant microemitters. So space is now, it is certainly the next frontier for optical communication.
Absolutely, and with the networks of communication satellites that are the next big thing. Inter-satellite communications using optics is of course well known because it gives you the bandwidth, but you still can't do the up and down link with optics easily because of clouds and so on. But maybe one day we'll figure out how to do that.
Yes. Now, Erbium, so EDFAs, they amplify, but they amplify a certain range of wavelengths. I think in the C band, I think around 1550, if I'm not mistaken. But I think you've been looking. Is there work to amplify other wavelength ranges as well, so we can tap into more of the spectrum?
Absolutely. Despite, as we have observed earlier, the enormous amount of fiber that's been installed and its incredible bandwidth per fiber, we're forever chasing more and more bandwidth. Because as fast as we put in fiber to satisfy the demand, somebody comes up with a new bandwidth-hungry application. Of course, the latest one being artificial intelligence, AI, which is scraping all the servers all over the world to gather its information, and this is really driving a bandwidth demand again. So one of the ways that you can increase the available bandwidth is to use different wavelength windows. Now, in conventional fibers, this is not that attractive an approach because the loss is by far the lowest at 1550 nanometers, the wavelength of operation that you mentioned. And so you go away from that, further into the infrared or shorter wavelengths towards the visible, the loss of the fiber goes screaming up. And yes, it's okay for short links, maybe in data centers, but not for telecommunications. However, and I'm sure we're going to talk about this in a little while, the new hollow core fibers, which have just appeared, have become wavelength agnostic. And so now you can make fibers which are pitched to much shorter or longer wavelengths. And this is opened up, and as I often called the tyranny of 1550, we no longer have it. We can think at different wavelengths. We can think about red wavelengths, and maybe even eventually down into the blue. But as you rightly point out, that requires wavelengths for amplifiers, different wavelength amplifiers. And it turns out that the erbium-doped fiber amplifier, although its primary attribute is that it actually works at the wavelength window of lowest loss in silica, is matched by a number of other wavelength amplifiers, such as the thulium-doped amplifier, and there are several others, the holmium-doped fiber amplifier, and they work extremely well. And some would say even better than the erbium-doped fiber amplifier. So we do have fiber amplifiers to match the wavelengths which are emerging with hollow core fibers.
We'll definitely talk about hollow core fibers later, because that's the creme de la creme. It's hugely interesting. It's one of the rare situations where I actually got goosebumps earlier this year at OFC when that recent breakthrough was announced by Francesco Pelletti. But one small digression, since we're talking about amplification. One thing you invented was the single mode silica fiber laser, and this is, I think, not for communication. This is for conveying very, very high optical powers. I think you broke the kilowatt barrier, many years ago. And I was wondering, how much power can we send over fiber today?
I think the world record, which I think was IPG company, is in the region of 15 kilowatts. per fiber. And that's in a solid core fiber, of course, because fiber lasers tend to be solid core fiber because you need somewhere to put the dopant, of course, and that's in the core. So I think the answer is in round terms, about 10 kilowatts per fiber, which is a staggering number. Because actually, when I first started working this, I looked up the books, of course, and the textbooks all said that should be closer to a few hundred watts. But the textbooks were wrong. And, we're an order of magnitude above what the textbooks would tend to tell you about the breakdown of silica glass itself with power.
It's extraordinary. What is the limit? I mean, how much power at which point would a single fiber melt?
Well, it tends to, it's not so much melting, although it can be. Melting comes from heat, of course, and you don't get much more heat resistance than silica. It tends to be breakdown, and also it tends to be at the splices, because I've often remarked that a fiber laser company is actually a fiber splicing company, because it's the fiber splices which are the hard part of the whole thing. And of course, if you get a little bit of leakage in a 10 kilowatt fiber laser of just a fraction of a dB, that's an awful lot of watts at that point. This brings us back, of course, to the hollow core fiber, because we've been able to demonstrate multi-kilowatts of transmission of power in a hollow core fiber as well. And that's got a lot of people's interest, because it means that potentially you could deliver an awful lot of power over, say, 100 kilometers and power something. I mean, it's not an alternative to power lines, of course not, but there are applications where you might want to remote power, for example, an amplifier or a sensor or something like that on an island or under the sea. And it's opening up that possibility as well.
Now we've mentioned hollow core fiber a few times. It is an incredible modern innovation for a reflection of the future of the internet. I know there's been the technology or the photonic bandgap fibers were invented a very, very long time ago, but only very recently these new designs by ORC, these NAMP fibers, these DNAMP fibers, have allowed incredibly low losses, lower loss than the lowest solid core fiber, which is an incredible milestone. I think that was reported earlier this year. Please tell us about how ORC came to develop these fibers.
Well, the history of that is interesting, because it stems back to the time when Philip Russell, who's widely regarded as a pioneer of the hollow core fiber, in particular the photonic bandgap fiber, was at Southampton, and so the first fibers were made at Southampton, and he then moved to Bath, where he did amazing work developing different designs. But the real breakthrough came with the so-called, you mentioned it already, NANF, the anti-resonant design, which are like nested tubes inside the core of a fiber. And these, apart from being much simpler to make, have the amazing characteristic that the light is expelled out of the glass by the anti-resonance. That's why they're called anti-resonant. And so very small amounts of light are present in the glass structure, which is performing the guidance. My colleague Francesco Poletti sometimes describes this as the bars of a cage which are holding the gorilla in. That means that all the power is contained in the quite large core, and this means that you become independent of the structure of the fiber, and you effectively potentially got the losses of vacuum, which of course are almost negligible, if not negligible. So this is what led to the breakthrough, and the design of those fibers is what Southampton has pioneered in, with David Richardson, my colleague, leading a big group, which was funded by EPSRC. And they formed a company called Luminicity as well, which was a great thing to do, because to be able to produce the quantity of fiber and get it out there into the world, you've got to have a company that can do it. And this company, of course, was acquired by Microsoft about 18 months ago, which shows you what the importance that they put on the invention of these ultra-low loss fibers. The current figure is the lowest loss that has been measured is below 0.1 dB per kilometer. And people are projecting that should get down to about 0.05 dBs per kilometer if you theoretically add up all the known loss mechanisms. And when you think about it, that would allow 1,000 kilometers without an amplifier. So I think my ambition is to eliminate the EDFA.
One of the great other characteristics of hollow core fiber is, of course, the speed of light. Solid core. Everyone says light is so fast, but in a solid core fiber, light is traveling at 2/3 the speed of light in a vacuum. But in a hollow core fiber, you're traveling at the speed of light in a vacuum. So that means light takes 50%. Latency is reduced by about 50%. And I remember working in the hyperscale industry. We were developing system-level optical interconnect devices, and we were toying with the side. We had hundreds of meters of fiber, and there are various protocols which have what are called time of flight restrictions. So you need a certain tiny, minuscule amount of time, for something to be transferred to another node, another CPU, before other problems come into play. So even sending light over hundreds of meters of solid core fiber can be limiting, but the ability to send it much faster over hollow core fiber means you can expand the distance between these different nodes, and that might be one of the reasons that Microsoft has such an interest in this low latency.
No, you're absolutely correct. Putting it crudely, it's just the refractive index of air or vacuum is lower than that of glass, and latency has come to. We are at a point, amazingly enough, where the size of the world has become a problem. It's just it takes time. Even the speed of light, it's too slow. And there are people that care about these, and you mentioned the data centers and so on, where it's critically important. But even things like gamers, it really is important. And you shrink the world with hollow core fiber. Everything seems a little closer than it does otherwise. And that's important. And it's important to people like traders, because automated computer trading, it depends upon how close you are to the stock exchange. And so the initial sales of the fiber have been very much into interconnecting the traders to the stock exchanges, because that brings them closer, which is a lot cheaper than moving your entire office and exchange.
So, yes, I remember. We were having a discussion. I think I just remembered as you were saying that we were having lunch together at one of the Photonics, and we were talking about how can we refer to different nomenclatures rather than photonics. And I think we talked about optics for banking to account for this for the nanoseconds the nanoseconds of difference that this hollow core fiber can make, and how critical that is to traders and banks. Yeah,
no, absolutely. And the hollow core brings the the confluence of a large number of attributes, because as well as the fact that the delay is less, it also, of course, has incredibly low nonlinearity. And therefore, you can put more power in, which we've already discussed, the amount of power that you can put down the fiber. But in the telecommunications field, that's incredibly important, because the normal limit to a solid core fiber that limits the amount of bandwidth you can get out of the fiber is, in fact, the nonlinear mixing between all the channels. And that is virtually non-existent in a hollow core fiber. So we're expecting to be able to get much closer to the theoretical limits with the hollow core fiber.
That's why, and that is very exciting. I mean, really pushing those limits. And I'm greatly looking forward to seeing how much you can approach absolute perfection over the next years for that. So it's going to be exciting when these hollow core fibers start to enter general circulation. I know it's now probably like hen's teeth, but when these fibers start to longer lengths start to be fabricated and deployed, it's going to really change the world.
Yes, I would agree. As I pointed out, the specialist applications such as installations in London, which they are carrying live traffic at the moment. There are a number of installations around the world. I believe there's one coming up interconnecting the exchanges in Shenzhen and Hong Kong, again, where latency is super important. As my colleague Francesco Poletti points out, there's a remarkable mirroring of the development of solid core. And this is wonderful, because you and I, Richard, both know then what's going to happen, because we were around at the time when the solid core was rolling out. So we know that the next steps are going to be the scale up and the cost reduction of these devices, the final tweaking of the designs, and then a range of specialist applications for hollow core fiber. And we're beginning to see these developing right now. So, for example, the gyroscope, which currently uses a solid core polarization maintaining fiber in a Sagnac configuration. And we've published some work with our sponsors in Honeywell on resonant gyros, fiber gyros, which is very difficult to do in a solid core fiber, because the fiber, in general statement, is limited by nonlinearity in the core. And tiny though that is, a lot of development effort for solid core fiber has gone into overcoming that nonlinearity, which produces an asymmetry and an offset in the gyroscope. And of course, these virtually don't exist, the nonlinearities in the hollow core fiber. So a lot of people are working on that for much improved gyroscopes of the future, navigational grade gyros.
So one other area is one other critical area. We've spoken about the interconnects, the fibers being the interconnects for transmission, but the endpoints. Southampton OSC has been a critical player in developing photonic integrated circuits, silicon photonics, and these silicon photonics started off as an academic curiosity many years ago. Now the silicon photonics forms the basis of all modern transceivers that you'd find in a hyperscale data center. I mean, this is what can you tell us about photonic integrated circuits and where we'll be going, what we'll expect to see in the future?
Yeah, so this is, of course, been pioneered by my colleague Graham Reed initially at Surrey and now at Southampton, where he moved about 15 years ago, if I remember correctly, along with his team. It's a very exciting integration technology, because the degree of integration that occurs in photonics is sadly not anywhere near as much as we would like it to be. And most people would agree that it's integration which gives you the cost reductions. Integration in optics is hard because there isn't the equivalent of silicon in electronics. Where every microprocessor on the planet is made from silicon microcircuits. And as a consequence, it tends to be a hybrid integration of different material systems, and that is very limiting. And you mentioned earlier, actually, when I think of one of the most exciting developments is the use of quantum dots on silicon photonics to overcome the fact that nobody's yet successfully made an emitter in silicon, an optical emitter in silicon. And that has been limiting the field because you had to do this, as I mentioned, hybrid. So you had to pick and place 3-5 chips for lasers and light sources and amplifiers and so on. And that's not a cheap technology because of the alignment requirements and so on. But we are making some serious progress there. And I think people are also coming up with multi-material platforms where you are able, well, we already mentioned the quantum dots, but there are other technologies that people are working on to be able to mix, for example, silicon nitride with silicon. Silicon itself is, and I always kid my colleague Graham Reed about this, silicon itself is a lousy optical material, okay, compared to silica, the oxide. We love the oxide. We've already mentioned that 100 kilometers is possible, but for silicon itself, you're talking about millimeters, centimeters. And, we'd like to overcome that problem as well. So it's a very exciting area. And as you said, we have a large team at Southampton, and there are other large teams around the world, Europe, US, China, Japan, all working on this integration in the hope that one day we will have little chips that cost tens of dollars maximum. We're a long way from that at the moment.
So one other area connected as part of this whole ecosystem of data processing, data communication. There's also data storage. And one excellent innovation from ORC is what's referred to as 5D optical storage. This is optical storage in glass, very dense storage, but the key characteristic of this is that the length of time over which you can store information, which I believe is close to the age of the universe, if I remember correctly. What can you tell us about this technology?
Yeah, I love this technology. This was developed by my colleague Peter Kazansky, and he's been working on this for 20 odd years. So it's not kind of an overnight sensation. But the concept is that you create little tiny, what we call voxels, with a focused laser in the substrate, which is once again silica. So you take a little chip of silica and you focus a high power pulse laser onto it, and this creates a tiny void inside the glass. They're a little like you may have seen these consumer commercial plastic blocks where you can write your kid's picture in it or something like that. It's not a million miles from that. But there are some differences. So what Peter Zansky found was that these little tiny voids had a characteristic, which we call birefringence, whose direction depended upon the polarization of the light that wrote it for reasons which are still not perfectly clear. And as a result, you got an additional dimension. So you mentioned that this technology is called 5D, standing for 5 dimensions. And what are those dimensions? The three are X, Y, and Z, as usual. but an additional 2 dimensions are obtained because of the directionality of the polarization of the light that writes these little voxels, these voids. And the 5th dimension is the strength of the birefringence of these little tiny voids can also be measured. So this gives you 5 different parameters, and this immediately, of course, gives you a much larger data storage capability. And then there's one additional thing, because this is a very highly nonlinear approach, you can write multiple layers. So each layer of these voxels, a little bit like the tiny little pits in a CD, but you can write, and I think Peter has written up to 200 layers of these. And because you can write through the previous layers and you can read through the previous layers. And you mentioned the headline, which attracts so many people, which is that because it's silica, it will last for billions and billions of years. In fact, the world is about 4 billion years old, so it'll last much longer than the age of the Earth up to now. Unless, of course, you accidentally drop it when it will shatter. But of course, what Peter Kazansky loves demonstrating is that you can take a Bunsen burner and you can heat these up to these chips up until they're red hot, and they still work perfectly well. And so this is what is called archival storage, which is, as you point out, incredibly important, because we've talked up to now about the ability to transmit these huge quantities of data around the world and the data centers which store them. Currently, the storage is done in archival storage in tape units. And this is 50-year-old technology. And the problem with tape units is that they need to be refreshed because they don't last forever. And that's a very expensive business to go back every 10 years or so and refresh all the data on the tape units. And this is archival storage, meaning that there are many things that you need to store forever, or at least for 50 years. And these are, for example, bank transactions and so on, and historical events which have to be stored, or even for a human lifetime. You won't like it if your pictures of your grandchildren are lost after 10 years, which you've stored up there in the cloud. So archival storage is incredibly important, and this, we believe, is the technology which solves this problem. And once again, Microsoft has picked up this work, is running with it in what they call Project Silica. And we understand that they are at a prototype stage. And we need to remember that ultimately you also need to be able to go and fetch these little tiny silica chips. And they've developed machines to be able to do that and go find the chips and bring them back in and read out the data if you demand it. And so it takes a few seconds to do that.
If you call, I used to work down the road, a stone's throw away from you in Havant in Seagate. And previously it was Xyratex, and that's all about data storage. And so archival storage was very important. We were in a project a long time ago with the BBC, and they had, as you mentioned, they had problems that they had all these, mountains of tape which were simply rotting away, and so much has been lost. So much very valuable information has been lost simply because the media has rotted away. I think one of the important things to really scale up this technology is the speed with which you can write data onto these silica blocks. How quickly can a machine write this information, and will this speed up in future?
Well, it is the one area where we need to improve. To give you an idea, if you want to write an archival copy of a movie at what I think is called the director's level of definition, which is very high indeed. It's higher than Blu-ray definition. It's going to take you a day or so. And although you do this, of course, with multiple machines, writing in multiple times, it could be faster. And there are many things that you can do, and we have done, and we are continuing to work on this to improve it. Once again, you've mentioned what we do at Southampton kindly on a number of occasions. A lot of what we do at Southampton is materials based. And I often say that in photonics, you never have the material you want, with the possible exception of silica. But there's an awful lot you can do on materials research. So is there a better material than silica for this application, the 5D archival storage? Is there a magic material or a magic dopant that you will put into the silica that will change everything and make it much faster to write? And we are working on that as we speak.
Now, one thing with from the photonic integrated circuit industry, one of the big challenges is how to couple fibers to photonic integrated circuit PIC chips, and this is done in a variety of different ways, vertically through grating couplers or along the edge. But one limitation I've heard about optical fibers is that standard optical fibers is that there's a limitation on how closely you can have put the fibers together to get the cores, because each core is in single fibers. Each core is surrounded by a certain cladding. But there are innovations to address this. There's multi-core fiber technology coming out. Is this something that you're working on in our ORC?
Yes. We've talked, I think we've hinted throughout this discussion that an ecosystem is required for each of the technologies that are emerging or are in the marketplace already. And I think there are those who believe that multi-core fibers are an important part of the future marketplace. But the question you asked, which is what about the splicing of them? And of course, it is more difficult than when you have a single core, because now you have to orientate during the splicing procedure. I take an open-minded approach to whether or not the multi-core fiber is going to make it in the marketplace. One part of me says, well, actually, the fiber is always dirt cheap compared to the total installation costs. Current costs for a kilometer of standard single core fiber is about $3 a kilometer, which I just find an incredible number. It's $3. Of course, it'll be much higher than that for multi-core, because most of the cost in a fiber is actually in the core anyway. And so scaling, you could argue that a 10-core fiber is going to cost 10 times as much. And then, of course, you need to be able to have amplifiers for each of the cores. And you really don't want to split them all out and have single amplifiers and then put them all back again. So we have published work on multi-core amplifier fibers as well. But all this is getting a little bit complicated and a little bit costly. And to what advantage? Well, there's a clear advantage if you have very full ducts, which some cities do have, and you don't want to put multiple fiber cables in because the duct is already full. And so the spatial density, if you like, of information in hollow core fiber in a multi-core fiber is of interest. But as I say, I've got an open mind on it, and I suspect that maybe some links will appear in multi-core fiber, but I suspect not many.
I tend to completely agree with you. One of the reasons I brought this up is that I chair a standards group in the IEC, a subcommittee on optical connectors, which is the largest standards group in the IEC, which reflects the fact that there are many experts part of this group, and for it to make it a standard, it has to be very well established. And only this year, I remarked upon how a huge number of multi-core fiber proposals seem to have emerged, most of them from Japan actually, including one for EDFA multi-core fiber from NTT, I think. And that's but I share with you, unless you absolutely need it, why would you the complexity of splicing two of these together, the rotational tolerances and so on would be, I would have thought they'd be prohibitive, but if they can manage to achieve it, that would be quite a feat of engineering.
And indeed, and if anybody can achieve that, it would be the Japanese.
Exactly.
So good luck to them, say I. And we have worked with a number of Japanese groups in this area, and so we have an insight into it. But it's interesting to see how the hollow core fiber impacts on that particular market, because it brings a number of other advantages which we've already discussed. You can, of course, make multi-core hollow core fibers as well if you wish, but that's a complexity that we're not even yet quite at the scale-up position where we'd like to be with the single core fiber. So that's for the future. But think of it this way, Richard, this is what pays our salaries, right? And as I pointed out earlier, we know what's going to happen because we just are following what happened for solid core fibers. So you can almost predict what you're going to be doing in 5 years' time.
Indeed. It's exciting. It's a very exciting time to be alive. Well, I mean, you can say that for the last 60 years, but it really is. It really is mind blowing. I wanted to just mention hyperscale data centers. All of this has related to, I think, in one respect or another, to hyperscale data centers, and this is the term we give for very, very large data centers, which typically comprise at least 100,000 servers, and they are used to administer cloud services. And now, increasingly, they're used to incubate AI clusters. So all the AI we hear about, the ChatGPT and so on, it's all incubated in these hyperscale data centers. And as of 3 years ago, hyperscale data centers are the dominant form of data centers. So and they really are critical to everything we do. But with the emergence of artificial intelligence, as I mentioned, ChatGPT, we've seen these kind of frivolous applications come up, which are very amusing. But the fact of the matter is, this wide-scale pattern recognition can be used for indispensable applications such as healthcare and preventative care and so on, and they can be a tool for incredible good. So it is. A lot of people say it's a bubble. I think it'll become too indispensable to be a bubble. So the relevance of this artificial intelligence in these hyperscale data centers is very important. But the hyperscalers, Microsoft, Google, Meta, are all saying the big problem there to make this optical is power consumption. And I think Microsoft, they are working. They hired a reactor on 3 Mile Island, and Google want to hire a nuclear reactor simply to power their data centers, because the power consumption of this is astronomical. And we're starting to see innovations such as immersion cooling, where you immerse the entire server into a mineral oil to really reduce your power consumption. So there's a strong pressure from the hyperscale to strongly reduce power consumption on all aspects. And one of the things we're seeing is for these networks and data centers is WDM communications, using different wavelengths of light in certain architectures. One architecture, for example, you have a tunable laser at a source, and you simply change the wavelength very quickly, and then it passes through passive filters like arrayed waveguide gratings to instantly give you move from one destination to another. And I think in UCL there was a spin out Oriola Networks, which is leveraging this kind of architecture. And I think Southampton is also plays a large part in these kind of ecosystem. For example, arrayed waveguide gratings. What are your views on using these new WDM architectures for AI in the future?
I think this is an incredibly important topic, and most of us have been careering along, ignoring it for the last decade or so. And it was brought home to me recently when somebody mentioned in a talk I was at that a typical single cabinet in a data center takes a goodly fraction of a megawatt. A megawatt of. I just was stunned by that number, and not only that, but I've heard talks of predictions that the IT of the world will consume the entirety of all energy generation by about the year 2040. And this is obviously unsustainable. And what are we going to do about it? And very few people have had the insight that you just mentioned up to now to say, what about the energy consumption of that wonderful new device? We just talked about some amazing things like the archival storage and so on. What does it mean for energy consumption? Ought to now be a question that everybody asks whenever they see a new technology emerging. So there are some simple things apparently that we can do, which is just improve our cooling systems, which you've mentioned, and make them much more efficient, just as your electric vehicle does. It uses a heat pump instead of the old ways of doing things. But going back to the fundamentals, which is the point you were making, I think, which is to go and say, no, that's an unacceptable technology. We need to do better. And when I started to look into this, I realized that the way that we've structured the overall global communication system is not optimal. For example, we use an awful lot of wireless, and wireless is very energy inefficient because it sprays energy in all directions, of which you only receive a small amount, whereas optics is very focused on that tiny little fiber, and you use pretty well all of the light that you transmit. And this is why the whole global internet is structured with all the heavy lifting being done. The figure, I think, is 99% of all data is carried in optical fibers. And then wireless has its role, of course, as the last drop to your mobile phone or in your Wi-Fi in your home or whatever. But it is not the infrastructure. And it's very inefficient. So one of the things we could be thinking about is more optics, less wireless. And what does that mean? It means shrinking the size of the wireless cells and feeding them with optics as an obvious thing that we could be doing. Using less wireless masts than we do, which are, that seems the opposite of what you want to do with microcells. But the wireless masts themselves currently can take tens of kilowatts, which is an awful number. So this is not my area of expertise by any means, but I think we need to rethink the way that we structure the global internet and telecommunications generally, with a much greater focus on the energy consumption. And ways of doing that, for example, you've already raised, would be integration. There are those that are talking about having a disaggregation of microprocessors, electronic microprocessors with optical interconnects between them, which is not a new idea, but one of the things that I learned was that every idea has its time window. And if you're too early or too late, well, it's obvious if you're too late, you've missed the boat. But if you're too early, the other technologies which are required to achieve it might not be ready yet. And so it fails. So optical interconnects goes back to the 80s, actually, early 80s, where I was working on some optical interconnect problems. But we couldn't do it. We didn't have integration. So that's another way that we can reduce the power consumption of the internet. and many others that will emerge, I'm sure, because as you point out, this is a very fast-moving technology. But one thing we can be certain of is it will be based on photonics.
Absolutely. And one thing I don't think we've addressed it is we need fibers to convey large amounts of information, but the amount of information that needs to be conveyed is getting larger and larger all the time. Today we send we send videos and we send movies, and this takes up a lot of information. But what's the future of the internet? What if we do have an internet where virtual reality becomes, or augmented reality becomes more widespread, where we'd have to convey not just two-dimensional videos, but we'd have to convey the information, capturing an entire three-dimensional, constantly changing environment over this. So the question is the amount of information we can send over a fiber. And I know ORC and others like UCL have done a huge amount of work in increasing the information carrying capacity of a fiber through different multiplexing schemes like wavelength division multiplexing and QAM and so on. What are your views on how far we can push this?
I think we are pretty well at the limit and have been for close to a decade now on how far we can push a single conventional solid core fiber. We see every single one of the major conferences tweaking it a little bit and getting just a tiny little bit extra. And yeah, there are fundamental limits, of course, to the amount of information you can push down a fiber, determined by the wavelength window that you have. And we've already talked about opening up wavelength windows, and that would give us possibly another order of magnitude of information capacity per fiber. But that could only be done with hollow core fiber, because as we've already mentioned, the wavelength window in a silica core fiber is fixed and has been since the early 80s. So we are running out of bandwidth in conventional fibers. The hollow core fiber will satisfy that to some extent. And then when that is all over in another 20 years' time or so, and we've tweaked that as far as we can always fall back to more fiber, more and more parallel fibers, more and more cores inside a single fiber, which we've already mentioned. So we've got a lot of legs and a lot of runway yet before we completely saturate the capability of photonics. Happily, because what is going to happen, and there's a theme, I think, emerging here, Richard, which you've touched on, namely that it's the provision of the hardware and the capacity. And I think this applies in a large number of technologies, which generates the applications. It's not the other way around, as most people think. It's actually somebody wakes up one day and said, you know what? Look at all this bandwidth. We could use that, and we could be profligate, and we could do silly things. Like we could develop emails where we just send back a one-word answer, yes, and we copy the entirety of everything in the previous email back again to the sender. That's what this profligacy is about. If you don't have to think it through too much, then suddenly an application can appear. And using bandwidth in a wasteful manner is just the way things are, and long may it continue, frankly. I don't want to write an email thinking about, can I remove a word here because it's going to use too much bandwidth. And there are many examples of that. We want to send high definition television signals. We want to send our photos of our kids at very high definition. We want big screens to view them on. So profligacy in bandwidth is going to happen. But a key question, which a colleague of mine, Will Stewart, raised to me the other day, which our listeners might like to think about, is what is the next big application that's going to eat up bandwidth? Now, we talked about AI. What follows next? is somebody going to come up with a killer application which suddenly requires vast amount of extra data? Because up to now, in the history of the internet, somebody has done that. Cloud computing being a perfect example of that, and the sorts of things which you could never have done in the old days. You and I are possibly old enough to remember the good old dial-up internet, where it
Yes.
used your phone line and it went.
Yes.
And you wouldn't have thought about. You really did think about the number of words in your email in those days.
Yes. So, one thing that was mentioned was ECOC, the European Conference on Optical Communication, and that's celebrated its 50th anniversary. And I was actually sat next to Will Stewart. I had dinner with you there at the conference. I was sat next to Will Stewart when they played this song, which was very interesting. So completely AI generated. This song about they simply fed in the information about 50 years of light, and they played this and they manufactured this complete song from scratch that seemed like a real song. And also you yourself a couple of days ago you sent me someone fed in the information of your bio and a podcast between two fictional American podcasters was manufactured discussing you, and it was so unbelievably authentic. The power of AI in this is terrifying. It's terrifying that what can be achieved, but it is, if you combine that with the possibility of virtual environments where you have these, and I'm not sure this is a utopian vision, but where you have these vast virtual realities where you have to convey information for depicting a moving, constantly changing environment shared by everyone. That would astronomically eat up bandwidth. I don't know if that's a good thing, but that might be where your next bandwidth hog is going to come from.
And of course, you're absolutely right. And I too are quite stunned by the capability of AI. But what we haven't touched on quite yet is machine learning in photonics, because another application of going back to my theme, it's always about the hardware, and the hardware in this case was the GPU, the graphics processors, which have come on in leaps and bounds, because the origins of AI. I remember when I was doing my PhD back in the early 70s, we were using optimization algorithms for intractable problems just to find a solution for simple things. But of course, at the time, it was limited by the ability to have these clusters of very high-powered GPUs. So once again, it's the hardware that changes everything. And then along comes the algorithms and that you put onto them. And I don't think we've really scratched the surface yet. So to get back to my point, what can machine learning do for the way that we use photonics? The design of, for example, a low energy network. And there are a number of people beginning to work on this and decide what the optimum structures are going to be. A piece of work which I know is going on and returning to the idea of a data center. What is the best way to communicate between all the elements of the data center, all the servers, with energy in mind, and starting with a blank piece of paper and with no technology on it whatsoever. So what's the best technology? Almost certainly, as we've agreed, it's going to be photonics, but what wavelength? And nowadays we've opened that space up. So, and what are we going to use for the transmitters, which in optics is often the energy consuming part? And what are we going to use? How do we get rid of the ASICs on the incoming fiber communication links to which are to the data center? Because those ASICs, which are correcting the impairments in the communication medium, are very power hungry. And so can we use machine learning to look at all of this and learn how to make the optimum low energy consuming structure? And I have a colleague of mine called Ben Mills at Southampton, who's a young and upcoming genius in AI and machine learning. And he just is staggering all of us because he just tends to wander into a room and say, is that the way you do it at the moment? Is that the way you make things? Just give that to me. I'll put a machine learning algorithm on it and it'll come up with some better way of doing it. And
Wow.
we go going, oh God. So yeah, it's breaking all the rules and designing integrated circuits and in photonics. The next generation of those is a very exciting area, and we're currently using it, for example, in an algorithm for a project that we have on extremely high power lasers. By extremely high power, I mean a megawatt continuous.
Wow.
The applications of these are fairly self-evident in the defense area, but also in incredibly fast manufacturing. And to do that, you have to parallel up vast numbers of lasers. And because we've already talked about the maximum power you can get out of one fiber laser, but now let's talk about 1,000 fiber lasers, all being combined together. And that's a challenge because we know how to do that from a physics point of view. We know that we have to phase them together, and that produces a single beam. And it's a steerable beam, which is, of course, exactly what you want. But doing that phasing together in a way which is efficient and fast, because you've got a millisecond or something that you want to be able to phase all these lasers together. As a complexity problem, that's a very hard problem. But we've come up with ways in which you can do that using machine learning and an algorithm which will just lock them all together suddenly and very quickly. So that's just a beautiful example, I think, of the importance of machine learning in photonics.
Agreed. One other area is inverse design. Again, in the photonic integrated circuit field, people are they put in their requirements, and a design is created which fulfills those requirements, and the design can be completely counterintuitive. It can look like a chaotic mess, but actually it gives you the perfect optical transmission profile, and that's a lovely, incredible example of what's possible with it.
Absolutely. Machine-led design, wow, it's going to put us all out of work. Actually,
yes, exactly.
Well, the way I see it is somebody's got to be able to drive the machine learning device itself. So maybe there's room for us yet.
That's right. One hope I have actually is with the AI, there is this adage, garbage in, garbage out. So you'll always need a source of reliable expertise. Otherwise, you won't get anything sensible out there. So hopefully there'll be the need for human beings with proper expertise to continually refresh these large language models.
Definitely, there's hope for us yet.
Okay, I think that's. Thank you, David. I think I'll just finish up with one last question. What is a personal question? What's the future for yourself now?
Who can predict the future? I've stepped down as the head of the ORC in favor of my colleague Graham Reed, the silicon photonics expert that we talked about earlier. And I'm having a lot of fun because it means I don't have to do all the bureaucracy and all that kind of stuff that comes from being the director of the operation, which is, by the way, is about a 300-person operation at Southampton in photonics. So I tend to focus my efforts at the moment on enterprise. I've often observed that there's no point in doing research unless you could have a route to getting it into the marketplace and test it. Yeah, because there's all too many these crazy ideas that come up and a publication is made and that's the end of it. I've always felt it's important. We owe it, if you like, to our sponsors, to our governments, to use the funding that has been, it's taxpayers' money after all, that has been paid to us, and show that we can create jobs, wealth, and to the betterment of mankind, which the internet, of course, is a perfect example of that. And as a consequence, at Southampton, we have a dozen or so companies which owe their existence to the work at the ORC. And we have another 3 in prospect at the moment. And because I've been involved for many years in the transfer of technology from research into companies and into products, and I enjoy that. It's having a foot in both camps. And right at the beginning of this podcast, I pointed out that I had intended to go into industry, but got seduced by my professor to developing the fibers for the internet. And as a result, I said, well, okay, I'll stay in the university, but I think I have an idea, which is that I'll have a foot in industry as well. And that's been very exciting, and I've thoroughly enjoyed that. And so I can intend to continue to do that. And to be able to do that, the first thing you need is to work with incredible people. And I've often observed that my first rule in life is always work with people smarter than you are, and that includes the students that I work with. And these are young minds that are yet to be polluted with older people's thinking. So I find that hugely refreshing. And my style of working is actually to discuss in groups and just ping off everybody, because that way, we mentioned earlier the GPU cluster. That's the human equivalent of a GPU cluster. It's a group of really smart people bouncing ideas off each other, sharing them in an open fashion, and not being afraid to be wrong with stupid comments. And because and that's my environment. And to cut myself off from that and go grow roses is not something that I feel that I'm going to do anytime soon.
Excellent. And I'm looking forward to meeting you in a couple of weeks. Actually, David, you've kindly agreed to give the plenary talk at the conference I chair, British and Irish Conference on Optics and Photonics in the IIT. And I really appreciate the conversation we've had today.
Thank you so much, because this has been it's been an absolute pleasure, and it's a rare privilege to be able to chatter away with colleagues such as yourself and just bounce ideas around. So I hope our listeners have enjoyed it.
Thank you, David.
Just before I let the both of you go, I've got a couple more questions around career development and career progression and the industry and academic circles. The conversation that you and Richard have had, Sir David, is absolutely incredible. I honestly do not want to ask anything on top of these questions, but I've just got a couple of questions to close things out. So, and this is a question to the both of you, and hopefully opens up a discussion. What are the characteristics and skills in research, industry, and academia that have remained timeless? And what are the things that have changed recently? What are today's challenges?
On the basis of the discussion which has been about photonics, it leads me immediately to a favorite topic of mine, which is interdisciplinarity. Photonics is a multidisciplinary field. We need mechanical engineers, we need chemists, we need physicists, to name just a few. And we still tend to silo the way that we educate people. I'm not sure I have a better way of doing it, frankly. But when we hire people in the ORC, we don't care too much about what their background is, surprisingly enough. And some of the brightest people that we've ever had have been with non-obvious backgrounds, like mechanical engineering. For example, one of the main contributors to the hollow core fiber that we talked about was a mechanical engineer that we recruited, Greg Jassian. And it turned out he was the only person that knew how to take a look at the fiber drawing process and say, I can analyze that and come up with models which did. And up to then, we'd just been doing it with try this, try that, try the other. So it's very, very important to have those range of disciplines. And I think there is an increasing recognition in the education system that we need to do better. And even, I say even, that's probably not the right word, but to involve our colleagues in humanities. Because the characteristic of most scientists and engineers and inventors is that we kind of invent something and then chuck it over the fence and say, well, it's your problem now, not mine. Actually, we've seen how the internet can be abused, and maybe we should have predicted that. And it might have changed the way that we designed it, for example. So those are my initial thoughts in response to your question.
I tend to agree. The humanities comment is very important. I think, in many respects, scientists and engineers, we should be held to the same moral obligations that doctors are, and doctors have to swear the Hippocratic Oath, do no harm. The work we do has equally that level of impact on humanity. So ethical responsibility for how we design, I think that's important. You asked about what we consider timeless. In our one important thing is engineering. The UK is extremely strong in engineering. Of course, modern engineering is the UK has been the leading player there. But in the 80s, we went through this phase, starting with the 80s, where engineering became there was almost a stigma attached to engineering in the 90s in the UK, while other countries like Germany, countries around the world, engineers were treated as high professionals. In this country, in the UK, there was almost a stigma attached to it, which was really tragic. Because it is one of our proudest traditions. I'm glad to say that now, certainly in the last 15 years, this stigma is now lifted. The importance of hardware engineering, especially, not just software engineering, but hardware engineering, and that know-how is becoming appreciated again. And engineering in the UK is being seen as the asset as it is. And personally, in my company, I prize. We have 9 engineers. And experience is the most valuable. We have mechanical engineers, electronics engineers, and a lot of people ask me, well, is this something that you recommend after your PhD? In my case, I've said PhD is not a prerequisite. Experience is a prerequisite. So the German apprenticeship model that works so well for them in the 70s and 80s is bearing fruit. I think training up in these different areas and developing actual expertise is crucial.
I think that's very interesting, because it shows, for example, where the focus is, the need is, and where the direction is going towards as well. A second question I had, and this can be from both perspectives, given all of your experience between the both of you and individually. How do you perceive mentor-mentee relationships to be? How do you perceive your role as a mentor? Have you had incredible experiences both as a mentor and being mentored by somebody else? Do you have any stories, any anecdotes of these experiences from your careers?
It's a fascinating question, because I think just as human beings are incredibly diverse, their need or otherwise for mentorship is very different. And I've known people who really don't need any, or even resent any form of mentorship because they know where they're going and they want you're just getting in the way. These are fairly rare type of people, but I have known a number of people like that, and I've just enjoyed letting them get on with it. On the other hand, there are those who are perhaps what's the word I'm looking for? Less driven or have a personality which is less robust, perhaps, who benefit enormously from mentorship. And then there are also ethnic differences, gender differences. I have mentored a number of women, for example, who appear to really appreciate it for reasons which it's too big a topic for us to get into now. But I think to have somebody that's been there, done that, and show them the way, because many women are juggling with families at the same time, and their priorities are not always obvious to them. And a mentor that helps them through this and helps them to make career decisions. And I have many examples of that where I've said to a female in particular, well, where do you want to get to? And if they say, I'd love to be somebody that's really famous in the field, I said, well, okay, then I can tell you how to do it. But if they say, no, I want to spend more time with my family and I want a middle range job, which is not quite so demanding, I say, well, you're talking to the wrong mentor then. It's equally valid, I think, by the way, that choice. Yeah, and talking about the gender politics, I think women have an advantage that they have that choice, and then we should respect that. But equally, if they choose to go the route of I want to be number one, then there shouldn't be any barriers in their way.
Richard?
In my case, mentor, well, about 20 years ago when I started, 24 years ago when I started in Xilinx down the road from David in Heaven, I was, even though I came from a photonics background, I was mentored by a very stereotypical rough Glaswegian. You live in Glasgow yourself, Akhil, and yep. He taught me electronics, and he really put me through my paces. And today, that guy is my chief engineer at Resident Photonics. He's a good friend, and he's the best engineer I know. And I'm delighted that he is leading my engineering team in an office in Glasgow. And I can't stress enough the importance of having a good mentor to really you need someone with experience to show the ropes. That will always be the case. And exactly as David says, you have to have the right mentor for the right for the right ambition.
I think it's really interesting, those perspectives, because personally I have just started supervising my first 2 PhD students. So I'm at the other end of the spectrum where the students are looking forward to feedback, they're looking forward to advice, they're trying to build a multifaceted career. And I have very much the same conversations as you said, Sir David, because it's always sit down at the start or do this multiple times during a PhD where you go, which way do you want to head? If you want to go into academia, these are the things you need. If you want to go into research, innovation, and industry, this is where you have to go. So I think those sort of mentorship steps and advice is always useful. I've received the same as well at every stage of my career. So I think this input is really, really useful. To end, I'd like to, you might have already mentioned this in your conversation, but I think I'd like to end on this note. Listening to this conversation would be industry personnel, academics, would be students, early career researchers, postdocs of different backgrounds. If there's one single piece of advice you'd like to leave for them, what would that be?
Well, I'm going to use a quote for that because my interests, as I've pointed out, I'm a fairly unusual academic, which is the commercial as well as the academic and the research side, very advanced research. And the quote is, never confuse the art of the possible with the art of the profitable. Because a lot of academics tend to do that. And to learn that it's not the really fancy piece of physics you just did, it's whether the world actually wants it. And what price is it going to be? Those are the important things. And those are the difference between a successful entrepreneurial activity and a successful company, and one that fails early because nobody wants your products.
That's very good advice. I will have to heed that advice now, as I like doing the cool stuff in our company. We're in these different EU and UK projects, looking at quantum, looking at communication, sensors, and so on. And it's very, very cool. But I will have to make sure that the world needs it and that it's profitable. Otherwise, it won't last long. So that's very good advice. In my case, all I would say is I'll touch upon something that David remarked upon before: the importance of interdisciplinarity. If you're in a field, get to know people in different fields. And some of the greatest innovations I know have come from talking to people from completely different disciplines, and getting together and having a conversation about what we all do. That's incredibly valuable. So I say that's useful.
Fantastic. And I'll echo something that Sir David mentioned earlier as well. And this is something I received from a mentor of mine who you might know based at Glasgow, Professor Miles Paget. His advice was always, the people that you work with are almost more important than the work you actually do. If you enjoy going to work every single day, yes, you'll always do incredible work. This is something that you touched upon earlier as well. And I think that's incredible advice that I'll probably hold on to, and I should hold on to for the rest of my career anyway. So I'd like to thank the both of you for your time. This has been an incredible conversation. We've talked optical fibers, interconnects. We've talked about the internet, hollow core fibers, photonics, and Nobel laureates. If you haven't heard, we've also talked about intergalactic optical fibers. So that might be interesting to sort of look back on and listen to as well. And I'd like to also say I've had a dial-up connection that has ruined phone conversations because it's using the internet to go through the phone lines back in India. Thank you very much for your time. This has been an incredible conversation, and I'm very, very glad that every one of you in the audience has joined in to listen to this conversation. Thank you so much. Have a wonderful day ahead, and see you next time.